Inside a ring of metal the size of a small house, a single particle is spinning. It lives for barely 2 millionths of a second, then it dies and flings out a smaller particle as it goes. Count those cast-offs, time them, and you can read how fast the first one was turning. The particle is a muon, a heavy cousin of the electron, and what you are reading is its wobble. Do this billions of times, and one number falls out. It sits a little above 2. Physicists have chased that number for more than half a century, in 3 countries, on 3 different machines. Every time it comes back the same, and every time our best theory of everything that exists has strained to explain why it lands exactly there. For a while, that steady little gap looked like a door into something new. Lately, it has started to look like something worse. There is a room in Illinois where a single particle runs in circles. It is too small to see and too quick to follow, and it does not last. It enters a ring of metal about 50 feet across, sunk inside a strong magnetic field, and it starts to turn. Not just around the ring, though it does that too. It turns on the inside. It spins like a tiny top, and as it races around, the direction of that spin slowly drifts. That drift is the whole story. The people who study it call it precession. You can call it the wobble. The particle never lives long enough to watch for more than a flicker. In about 2 millionths of a second, it falls apart and throws out a lighter particle as it goes. That cast-off flies off in a direction set by which way the top was pointing when it died. So the team does not watch the wobble directly. They catch the wreckage. They count where the pieces land and when, billions of times over, and from that rain of endings, they rebuild exactly how fast the spin was turning. Out of all of it comes one number. It says how strong a magnet this little particle is. By the oldest form of the theory, that number should be exactly 2. It is not. It sits a hair above 2 by about 1 part in 1,000. That hair is the point of everything that comes next. Here's what should not sit easily. This is not some fresh result. People have been pulling this same number out of the dark for more than half a century. They have done it on 3 different machines, in different countries, with tools that improved beyond recognition along the way. The first ones used borrowed magnets and hand calculation. The latest reads the wobble to better than 1 part in a billion. Across all of it, separated by whole careers, the number keeps landing in the same place. A result that repeats is supposed to be a comfort. In science, a thing you can measure over and over is a thing you can trust. And here the trust is total. This measurement is as solid as anything in physics. That is exactly what makes it strange. Because the number is not only a fact about one particle, it is a kind of grand total. When this particle wobbles, it is answering to everything around it, including things that are barely there at all. So the wobble is meant to add up every force and every particle that exists, the ones we know and the ones we do not. For a long stretch, when physicists ran that sum on paper, the answer they got did not match the answer the particle kept handing them. The particle wobbled a touch more than the math would allow, a small gap. The same small gap, again and again, and for years that gap looked like the most thrilling thing in the field. Because a particle that wobbles more than the rulebook permits is a particle telling you the rulebook is missing a page. Maybe a force nobody has felt. Maybe a particle nobody has caught. The particle is the muon. The ring in Illinois is only the latest place it has been put to the question. What no one has managed to put to rest is why this single number refuses to match the math and refuses to move, no matter how carefully anyone checks. Any answer has to begin with the witness, because nothing else in nature would hold still long enough to be asked. Right now, as you read this, particles are passing through you. They started high above your head, miles up, where a piece of debris from a dead star slammed into the top of the air. That crash threw off a spray of fragments, and some of those fragments are raining straight down through the roof, through your body, and into the ground. About one of them goes through your hand every second or so. You feel nothing. They barely notice you are there. These are muons. A muon is a heavier copy of the electron, the same particle that flows through every wire in your home, but about 200 times as heavy. It carries the same kind of charge. It spins the same way, it just weighs far more, and that extra weight changes its fate. An electron, left alone, lasts forever. A muon does not. After about 2 millionths of a second, it comes apart on its own and turns into lighter things. You would think a particle that dies almost the instant it is born would be useless. It is the opposite. The muon is one of the best messengers we have, and its short life is part of the reason. Start with the weight. Because the muon is so much heavier than the electron, it reaches deeper into the strange world of things that flicker in and out of empty space. A heavy particle feels the pull of other heavy things far more strongly than a light one does. If there is some unknown particle out there, too massive for us to make directly, the electron would mostly shrug it off. The muon would feel its tug. That makes the muon a kind of fishing line dropped into water we cannot otherwise reach. Then there is the spin. A spinning charge is a tiny magnet, and a tiny magnet in a strong field cannot help but wobble. The rate of that wobble depends on the exact strength of the magnet, and the exact strength depends on every little thing the particle brushes against. So the muon turns its own private life into a signal we can read. And the dying, the part that sounds like a flaw, is what lets us read it. When a muon falls apart, it does not throw its debris off in random directions. It tends to fling the lighter particle along the way its spin was pointing. So the direction of the wreckage is a pointer. Catch enough of that wreckage and you can tell, with brutal precision, which way the top was facing at the end. The death is the readout. Put those together and you have a witness with rare gifts. It is sensitive to things far heavier than itself. It writes its experience into a wobble, and it confesses everything in the act of dying. Nature seems to have built a particle whose entire short existence is a measurement waiting to happen. That is why this one corner of physics has eaten up 6 decades of effort. People did not chase the muon because it was easy. They chased it because it was honest, and because the thing it kept confessing did not line up with what the theory swore should be true. To understand why a wobble could shake the foundations of physics, you have to go back to the number 2, and to the moment someone realized it was not quite 2 after all. Almost a century ago, a quiet British physicist named Paul Dirac wrote down an equation. He was trying to describe the electron in a way that respected both the rules of the very small and the rules of motion near the speed of light. The math was elegant, and it did something he never asked it to do. It predicted on its own that the electron should behave like a magnet of a very particular strength. In the units physicists use, that strength came out to exactly 2. This was a triumph. Out of pure theory, a clean whole number. For a while, 2 looked like a fact carved into the floor of reality. It was not. Within a couple of decades, an American physicist named Julian Schwinger went back to the same problem with sharper tools, and he found that the number could not be exactly 2. It had to be a little more. The reason is one of the strangest ideas in all of science, and it is true. Empty space is not empty. What we call a vacuum is actually crowded. particles wink into being and vanish again before they can be caught, borrowing energy from nothing and paying it back almost instantly. They are there and not there at the same time. Physicists call them virtual particles, but you can think of them as a faint, restless static that fills every gap in the universe. An electron is never truly alone. It moves through this static, and the static tugs at it. Now and then, it spits out one of these fleeting particles and swallows it back. Each of those small acts changes by a sliver how the electron responds as a magnet. Add up all the slivers and the magnet strength creeps above 2. Schwinger worked out the size of the first and largest of those slivers. It was tiny, a bit more than 1 part in 1,000, and when experiments went and measured the real electron, that tiny extra was there, almost exactly where his math said it should be. The number on his chalkboard matched the number in the world. It remains one of the proudest agreements in the history of physics. That little extra got a name: the anomalous magnetic moment. You can drop the long words and just call it the extra, or the anomaly. It is the gap between the plain prediction of 2 and the true value the universe insists on. And here is why it matters so much. That extra is not noise. It is a record. Every kind of particle that can flicker in and out near our magnet leaves its mark in the size of the extra. The static is made of everything that exists. So if you can calculate the extra and measure the extra and compare them down to the last digit, you are checking your entire list of what the universe is made of against the universe itself. For the electron, the 2 numbers agree so well that the theory looks almost perfect. But the electron is light, and it barely feels the heavy, hidden things. To put real pressure on the theory, you want a heavier version of the same particle, one that wades deeper into the static and feels more of what is hiding there. That particle was sitting right there, raining down from the sky. All anyone had to do was catch it, hold it still in a magnetic field, and read its extra to the bone. That turned out to be far harder than it sounds, and the first people to truly pull it off were working with a magnet they had borrowed from a university in England. More than half a century ago, on the edge of a lake between France and Switzerland, a new laboratory was finding its feet. It had been built so that the countries of Europe could chase the smallest pieces of matter together, instead of apart. In its early days, it had one accelerator and a great deal of ambition. What it did not have was much equipment to spare. One of the ideas drifting through the place came from an American physicist named Leon Lederman. The muon had only recently been pinned down as a real and separate particle, and there was a question hanging over it that no one had answered. Did this heavy cousin of the electron carry the same little extra in its magnetism? Did it obey the same hidden static, or was it a different kind of thing altogether? If you could measure the muon's extra, you could test the deepest theory of the day in a place that had never been pushed. The trouble was that nobody had a clean way to do it. The muon dies in millionths of a second. You cannot trap it in a jar. You have to make it. Hurry it into a magnetic field and read its wobble before it falls apart. To even begin, the team needed a magnet with a very even, very steady field. They did not have one. So they borrowed a long magnet from a university in Liverpool and went to work. A small group of physicists gathered around the problem. They sent muons into the field and watched for the telltale pattern in the particles that came spraying out when the muons died. From the timing of that spray, they could read how fast the spinner turned. It was slow, painstaking work, full of ways to be fooled, and it worked. They published the first real measurement of the muon's extra, and it landed close to the prediction, within a couple of percent. Then they sharpened it. Before long, they had it down to a few parts in 1,000. The muon, they could now say with confidence, carried the same kind of extra as the electron. It lived by the same hidden rules. The deepest theory of light and charge had passed a test in brand new territory. This was the moment the muon became a tool instead of a curiosity. The team had shown that you could take the most fragile particle imaginable, hold it in a field, and squeeze a precise number out of its depth. The method was crude by later standards, but the path was now clear. Make the field steadier. Catch more muons. Read the wobble more carefully. Each step would let you see deeper into the static and feel more of whatever was hiding in it. So they did not stop. They built bigger and better versions, each one reaching for more digits than the last. With every gain in precision, the measurement turned from a simple yes or no into a true probe, sensitive enough to start counting the contributions of particles one by one. That ambition carried a quiet risk, and almost nobody saw it coming. As the measurement grew sharper, it was bound to reach a point where the simple version of the theory could no longer keep up. The particle was about to start telling the theorists something they did not want to hear. But to feel why that mattered, you have to understand what the wobble is really counting, and just how much of the universe is folded into a single number. Picture the muon again, racing around its ring, spinning as it goes. It looks alone in there. It is not. It is wrapped in that restless static, the haze of particles that flicker into being and vanish again, and it is constantly trading tiny touches with them. Each touch nudges its wobble by a sliver. The full size of the extra is the sum of every one of those slivers. Now think about what is in the haze. The lightest and most common visitors are particles of light, and the electron's own ghostly copies. They are easy. Their contribution can be calculated to a staggering number of digits, and it makes up the bulk of the extra. This is the part the theory handles beautifully. But the haze is not only made of light things. Now and then, heavier visitors appear. The particles that carry the weak force, the ones responsible for certain kinds of radioactivity, take their turn near the muon and leave a faint mark of their own. They are rare guests because they are heavy, but the muon is heavy enough to coax them out, and their fingerprint is there in the number if you look closely enough. Then it gets harder. The haze also fills at times with the particles that feel the strong force, the ones that make up the hearts of atoms. These come in swarms, gripping each other so fiercely that the usual tricks for adding up slivers break down. This part of the static is a storm, not a drizzle, and it is the single most difficult piece of the whole calculation. Hold on to that. It becomes the hinge of the entire story later on. Here is the thing that makes the muon worth 6 decades of obsession. The haze is made of everything. Every particle that exists, no matter how heavy, no matter how shy, can in principle flicker near the muon and tilt its wobble by some amount. So the extra is not just a number about a muon, it is a tally of the full contents of reality. Measure it precisely enough, calculate it precisely enough, and you are holding the universe's own inventory up against your own and checking it line by line. And this is where the muon's weight pays off. A particle that is heavier reaches further into the haze and feels the heavy hidden things more strongly. The electron is too light to notice them. The muon is heavy enough to be tugged. If there is some new particle out there that we have never made and never seen, too massive to appear in any machine we have built, it would still be lurking in that static. And it would still lean on the muon's spin. It would push the extra away from where the known particles alone would place it. So the plan, in plain terms, is brutal and simple. Add up the slivers from everything we know about. That gives you a prediction. Then measure what the muon actually does. If the two agree, our list of the universe is complete, at least as far as the muon can feel. If they disagree, something is leaning on the muon that is not on our list. Something is out there, hiding in the haze, making itself known only through the wobble. For a long time, the two numbers did not agree. The muon wobbled more than the known universe could account for. And the first hint that the simple math was not enough did not come from some exotic machine of the future. It came when the early teams pushed their own measurement just past the point where the easy version of the theory could follow. For its first round, the muon hunt had it easy in one sense. The measurement was good, but not yet good enough to feel the storm. The number that came out matched a prediction built only from the light. Well-behaved parts of the haze, the particles of light, and the electrons' copies. Those parts could be calculated cleanly. The muon agreed with them. Everyone could rest. Then the teams got greedy, as good experimenters always do, and they made the measurement sharper. They built a new version with a far steadier field and caught many more muons, and the number tightened by a large factor. With that new sharpness came a problem that the earlier, blurrier result had hidden. The clean prediction, the one built only from the easy parts of the haze, no longer matched. The muon was wobbling a bit more than the light particles alone could explain. This was not a crisis. It was at first a clue, and a welcome one, because the theorists knew that their clean prediction was incomplete. They had left out the hard parts on purpose, the contributions from the heavy force carriers and the storm of strong force particles, because those were difficult to pin down and small enough to ignore while the measurement was still rough. Now the measurement was no longer rough. It had become sensitive enough to feel those harder contributions directly. So the gap was telling them something true. It was saying, in effect, that the muon could now feel parts of the universe the simple math had skipped. To close the gap, the theorists had to go back and add those harder pieces in. They had to account for the heavy force carriers. They had to wrestle with the storm of strong force particles, at least roughly. When they did, the prediction rose to meet the measurement, and the two came back into line. Read that again, because it is the pattern of the whole saga in miniature. The muon got measured. The measurement disagreed with the math. The math was not wrong so much as incomplete, and the disagreement forced the theory to grow until it could explain what the particle was doing. The muon did not break the theory. It expanded it. It pushed people to take seriously contributions they would rather have left in the too hard pile. By the end of that early era, the agreement was extraordinary for its time, good to a few parts in a million. The deepest theory of forces had been tested in fine detail by a particle that lives for less than the blink of an eye, and it had held. People moved on. The muon had done its job. The book, it seemed, was closed. But notice what had quietly happened. Every time the measurement got sharper, it reached a little further into the haze and felt a little more of the hard, stormy part that nobody could calculate cleanly. As long as the experiment stayed rough, that storm could be waved away. As the experiment grew precise, the storm became the whole game. The fate of the entire comparison, agreement or disagreement, now rode on the one piece of the calculation that no one fully trusted. That was a loaded situation, and the people who built those first machines had taken the muon as far as their tools could reach. To go further, the hunt would need a colder, larger, more perfect ring, and it would have to cross an ocean to find one. But before the relay left Europe, the early teams had quietly solved a problem that sounds impossible on its face. They had figured out how to hold a particle that refuses to be held. Think about what the measurement actually demands. You need a muon to circle inside a magnetic field thousands of times so its wobble can build up into something that you can read. But the muon barely lives. In 2 millionths of a second, it is gone. And it is moving at nearly the speed of light, which means in that sliver of time it would shoot in a straight line for hundreds of yards and be lost. To read its wobble, you have to bend that straight line into a closed loop and keep it looping until the particle dies. You have to build a cage for a ghost. The cage is the storage ring. It is a big circular magnet, and the field inside it curves the muon's path into a circle so the particle chases its own tail around and around. That part is straightforward enough. A charged particle in a magnetic field turns. The hard part is keeping it from drifting up or down and crashing into the walls before it has lived its full life. The obvious fix is to add a second kind of field, an electric one, to nudge stray muons back toward the center. And here the trap springs a problem of its own. An electric field does not just steer the particle, it also disturbs the very wobble you are trying to measure. Push on the muon to keep it in line, and you corrupt the number you came for. For a while, this looked like a wall. You needed the electric field to hold the beam, and you could not afford what it did to the spin. The way through is one of the quietly beautiful tricks in physics. It turns out there is a special speed, a particular energy you can give the muon, at which the disturbance from the electric field cancels itself out. At that one magic setting, the steering field still holds the beam in place, but its effect on the wobble vanishes. The particle can be pushed around the ring without lying to you about how fast it is spinning. You just have to tune every muon to that exact energy and let the cancellation do the work. So the recipe came together. Make a beam of muons, tune them to the magic energy, inject them into a ring with a steady magnetic field and a gentle electric one set to the sweet spot. Let them loop thousands of times, and all the while, ring the loop with detectors that catch the wreckage as the muons die, one by one, and note the direction and the timing of every death. Out of that grim census comes the wobble. The directions of the debris swing back and forth in a slow rhythm as the spin drifts around, and the speed of that rhythm is the number. The longer the muons live in the ring, the more swings you see, and the sharper you can pin the speed. Everything in the design serves that one goal: steadier field, purer beam, longer life in the ring, more deaths counted, more digits in the answer. This was the machine, in its bones, that the early teams handed down. A ring, a magic energy, a wall of detectors, and a method for reading the spin of a dying particle from the way it scatters its remains. The blueprint was sound. What it needed now was someone willing to build it bigger and colder and more perfect than ever before, and to point it at the muon long enough to see if that stubborn extra was truly where the theory said it should be. That someone was waiting on the far side of an ocean. The hunt left Europe and came to a flat stretch of Long Island, in New York, where a national laboratory had the space and the muscle to build something the earlier teams could only dream of. The plan was to take the proven recipe, the ring and the magic energy and the wall of detectors, and push every part of it to an extreme. More muons, a steadier field, and above all, a ring built not from ordinary magnets but from coils chilled until they lost all resistance to electric current. That last choice is what set this machine apart. A coil chilled close to the bottom of the temperature scale can carry an enormous current without wasting any energy as heat. And a huge, steady current makes a huge, steady field. The team wound such coils into a ring more than 40 feet across and cooled them down. And the result was one of the most uniform magnetic fields ever made over such a large space. Inside that ring, a muon could circle in a field, so even that its wobble would stay clean for thousands of loops. They knew the field had to be mapped to a fineness that bordered on the absurd. The whole measurement compares two rhythms: the speed of the muon's wobble and the strength of the field it is sitting in. And the answer is only as good as your knowledge of both. So they sent probes through the ring again and again, charting the field at point after point, hunting down every faint ripple and bump. A flaw in the field that no one noticed would show up in the final number as a fake signal, a wobble that was not really there. Then they ran it for years in patient campaigns. They filled the ring with muons, let them die, and gathered the rain of wreckage in detector after detector. They did it with positive muons and with their negative mirror partners, to check that nature treated both the same. They pulled in an enormous pile of data, far beyond anything the early teams had managed, and slowly the number sharpened. And as it sharpened, something began to surface that had not been clear before. The muons extra, measured here in this colder and more perfect ring, did not sit quite where the theory placed it. It sat a little above, not by much, by a sliver on top of a sliver. But the measurement was now precise enough, and the prediction careful enough, that the small difference could no longer be shrugged off as fuzziness in the tools. This was a different kind of gap from the one the early teams had seen. Back then, the disagreement came from a prediction that was knowingly incomplete, missing its hard parts. This time, the theorists had done their best to include everything: the light parts, the heavy force carriers, even their finest guess at the stormy, strong force piece. They had built the most complete prediction they could. And the muon still wobbled more than that complete prediction allowed. A gap that survives your best effort to close it is a different animal. It stops looking like a hole in your homework and starts looking like a hole in the world. Either some unseen thing was leaning on the muon, or the storm in the calculation was hiding a mistake. Both possibilities were enormous, and the team had to be ruthless about which one they were really seeing, because in this game, a small gap is the easiest thing in the world to fool yourself about. So a gap had opened. The muon wobbled a little more than the fullest theory could explain. The natural reaction, the human reaction, is to get excited. The careful reaction is to ask a colder question. How sure are we that this gap is real, and not just luck? Every measurement comes with a wiggle. Run the same experiment twice and you will not get the exact same number, because there is always some randomness in how many muons you caught and how they happen to die. So a result is never a single value. It is a value plus a fuzz, a little cloud of uncertainty around it. The prediction has its own cloud too. The question is whether the two clouds overlap. If they do, the gap might be nothing. If they sit clearly apart, the gap is starting to mean something. Physicists measure that separation in steps, and they have a word for one step of the cloud's width. They call it a standard deviation, or sigma. You do not need the math, just hold the picture. 1 sigma of separation between measurement and prediction is nothing to write home about. That happens by chance all the time. 2 sigma raises an eyebrow. 3 sigma gets people whispering in hallways. But whispering is all it gets, because the field has been burned before. The reason for the caution is that flukes are common when you look at enough things. A 3 sigma bump has a real chance of being a trick of the randomness, and the history of physics is littered with 3 sigma bumps that excited everyone and then melted away when more data came in. So the community drew a hard line in the sand. To call something a discovery, to say a new piece of reality has truly been found, you need 5 sigma of separation. At 5 sigma, the odds that the gap is pure luck fall to about 1 in 3.5 million. That is the bar. Below it, you do not have a discovery. You have a hint. The muon's gap, as the Calder ring first revealed it, sat at roughly 3.5 steps. 3.5 sigma. Enough to make a lot of very serious people lean forward. Not enough, by the field's own iron rule, to claim anything at all. It lived in the worst possible place, too big to ignore and too small to believe. And this is where the discipline really bites, because at 3.5 sigma, there are 3 honest possibilities, and you cannot yet tell them apart. The first is that the gap is a statistical fluke, a roll of the dice that happened to come up high, and that more data would shrink it back to nothing. The second is that the gap is real, but it comes from a mistake somewhere, a flaw in the field map, or a soft spot in that stormy, strong force part of the calculation. The third is the thrilling one, that the gap is real and clean, and that something genuinely new is leaning on the muon from inside the haze. A weaker field would have called it a discovery and been embarrassed later. This one did not. It reported the gap honesty, with its size and its fuzz laid bare, and it left the door open on all 3 explanations. That restraint is the unglamorous heart of how physics protects itself from its own hopes. So the gap was real on paper, but unproven in fact. The only way to settle it was to measure again, harder, and to watch what the number did. And what the number did, over the years that followed, was the most unnerving part of all. The honest way to kill a 3.5 sigma gap is to feed it more data and watch it shrink. Flukes fade. A bump that came from a lucky roll of the dice gets smaller as you gather more, because the randomness averages out and the true value bleeds through. So the Calder ring kept running. It kept collecting muons. It kept refining the field map and chasing down every quiet source of error. Everyone, believers and skeptics alike, waited to see which way the number would drift. It did not shrink. It did not grow. It stayed. Every time the team added data and tightened their grip, the muon's extra settled back into the same spot, a sliver above the theory's best prediction. The cloud of uncertainty around it got smaller, which only made things worse for the comfortable explanation, because a fluke is supposed to wash out, and this would not wash. The more carefully they looked, the more firmly the gap held its place. When they finished, they had the most precise measurement of the muon's extra anyone had ever made, and it disagreed with the fullest prediction by that same stubborn amount. Not a discovery by the 5 sigma rule, but a hint that had refused every chance to disappear. A hint with staying power. Sit with how strange that is. A mistake in your tools tends to shift when you change your tools. A fluke tends to fade when you gather more. This did neither. It behaved exactly the way a real feature of the universe would behave. It sat there, the same size, no matter how hard anyone pushed on it, like a stone you keep stubbing your toe on in the dark. This is the moment the story stops being about one experiment and becomes about repetition itself. Going back to the very first hunts with the borrowed magnet, through the sharper machines that followed, and now through this cold and careful ring, the muon kept handing back a number that the known universe could not fully account for. Different teams, different decades, different tools, each better than the last, The same small, defiant gap. A number that refuses to lie is the most interesting thing a scientist can find. If a story built on one of those is the kind of thing you want to follow, subscribe and stay with it. Because the next turns are where it gets genuinely strange. The trouble was that a repeating result, on its own, cannot tell you which of the explanations is true. The repetition rules out a simple fluke. It does not rule out a shared mistake. If everyone was leaning on the same flawed piece of the calculation, then every team would see the same gap. Faithfully, forever. And it would mean nothing about new physics. The repetition would be real. The cause would be a phantom of arithmetic. And there was one piece of the calculation that everyone leaned on, and no one fully trusted. The stormy part. The contribution from the strong force. The swarm of particles that grip each other too tightly for the usual methods to handle. If a flaw was hiding anywhere, it was hiding there. So even as the measurements stood firm, the suspicion began to grow that the real mystery was not in the ring at all. It was on the page, in the single hardest number anyone in this field had ever tried to compute. To compare the Muon's wobble against the theory, you need a prediction, a single number built by adding up every contribution from the haze. Most of that sum is a pleasure to compute. The light particles and the electrons' copies can be calculated to more digits than you could read aloud in an afternoon, and the heavy force carriers, while harder, are under control. If those were the only pieces, the prediction would be as sharp as the measurement, and the comparison would be clean. They are not the only pieces. There is one contribution that turns the whole calculation into a nightmare. It comes from the moments when the haze around the muon fills with particles that feel the strong force, the same force that binds the cores of atoms together. In plain terms, the empty space near the muon briefly boils with the stuff that quarks and their glue are made of. And that boiling stuff tugs on the muon's spin like everything else does. The tug is small, but it is large enough that the final answer depends on getting it right. Here is why it is so hard. The strong force has a cruel personality. Most forces get weaker as particles move apart, which means you can treat the interactions one at a time, as a series of small, manageable touches. The strong force does the opposite. It grips harder the further you try to separate things, and up close the particles cling to each other in a dense, churning crowd. There is no quiet one touch at a time picture. There is only the storm. The usual method, where you add up slivers in order from biggest to smallest, simply falls apart, because none of the slivers are small. So this one piece, the boiling of the strong force in the vacuum near the muon, cannot be computed the easy way. And it is not some negligible footnote. It is the largest single source of uncertainty in the entire prediction. The light parts are known to absurd precision. The fate of the whole comparison, agreement or disagreement with the muon, hangs almost entirely on how well anyone can pin down this one stormy term. Take that in. After 6 decades of polishing the measurement until it could read a wobble to better than 1 part in a billion, the question of whether the muon agrees with the universe came down not to the experiment, but to a single, stubborn number on the theory side that nobody could calculate cleanly. The bottleneck was not the ghost in the ring, it was the storm on the page. For a long time, the only practical way to get that number was a clever sidestep. You cannot calculate the storm from first principles, so instead you go and measure it indirectly in a different experiment entirely. It turns out the same boiling of the strong force that tugs on the muon also shows up when you smash light particles together and watch what kind of strongly interacting debris comes out. By measuring that debris carefully across a huge range of energies, you can reconstruct the size of the storm and feed it into the muon prediction. It is a beautiful trick. It is also only as good as those other experiments, and it carries every one of their uncertainties into the heart of the answer. So the prediction the muon was being judged against rested on a tower of measured data about strong force debris, stitched together into one fragile number. As long as that tower stood, the gap stood with it. If the tower had a crack, the gap might be nothing more than the shadow of that crack. There was, in principle, another way to attack the storm, a way that did not lean on those other experiments at all, but it would demand machines of a different kind entirely. Before any of that could be settled, the experimental hunt itself was about to make a journey that sounds more like a heist than a measurement. The colder ring on Long Island had given the world its stubborn gap, and then its work was done. The team that built it had reached the limit of what their muon beam and their funding could deliver. To push further, you needed more muons and a purer beam, and that meant a different laboratory with a different machine to feed the ring. There was such a place, a national laboratory outside Chicago, in Illinois, with exactly the kind of beam the next round of the hunt required. There was only one catch, and it was a big one. The heart of the experiment was that enormous ring of superconducting coils, more than 40 feet across, and it had taken years to build and to coax into making such a perfect field. Building a new one from scratch would cost a fortune and risk never matching the original. So someone made a daring call. Do not build a new ring, move the old one. Take the giant magnet from Long Island and carry it more than 3,000 miles to Illinois in one piece. The problem is that this kind of ring cannot be taken apart and rebuilt like a piece of furniture. The coils inside it are wound and set in a way that holds the field's perfect evenness. And if you bend the structure too far, the coils crack, and the whole thing is ruined. The engineers set a brutal limit. Across the entire journey, no part of the ring could flex by more than a small fraction of an inch. A single careless jolt could destroy years of work. So they planned a route that babied it the whole way. They could not simply truck it across the country, because the roads would shake it to pieces, and it was far too wide for ordinary highways. Instead, they floated it. They loaded the ring onto a special carrier, eased it onto a barge, and sent it by water down around the coast and up through inland rivers, the slow way, where the ride is gentle. For the final stretch on land, they laid it on a custom truck and crawled it along closed highways in the dead of night, at a walking pace, with crowds gathering along the route to watch a giant white ring inch past in the dark. It was a strange public spectacle for something so technical. People who would never read a physics paper came out to see the Great Circle pass, wrapped and glowing under the lights, as if a piece of a spaceship were being delivered. And the whole way, sensors watched for any flex beyond the limit, any sign that the precious coils were under strain. The ring made the journey without harm. It arrived in Illinois intact. The same perfect circle that had measured the muon's wobble on the far coast. This was more than an engineering stunt. It was a statement about how seriously the field took that stubborn gap. You do not haul a 40-foot magnet across a continent on a barge to check a result you think is a fluke. You do it because the number would not go away, and because the only way to learn its true nature was to measure it again, with more muons and a cleaner beam, in a place built to push it harder than ever. Now the ring sat in its new home, waiting to be woken up. But before the team could trust a single number that came out of it, they had to do something that sounds almost paranoid. They had to make sure they could not see the answer, even as they spent years working to find it. A perfect ring is not enough. You can build the most uniform magnet in the world, feed it the purest beam of muons ever made, and still ruin everything with a far quieter enemy, the one inside your own head. The team that took over the hunt in Illinois understood that the greatest threat to the measurement was not a flaw in the field or a glitch in a detector. It was hope. It was the simple human pull toward the answer you were expecting to find. Think about the situation they were in. The whole world knew the previous result. Everyone knew the muon had wobbled a little more than the theory allowed, and everyone knew that if this new machine saw the same thing with sharper eyes, it would be one of the biggest results in modern physics. The people doing the analysis wanted that. Of course they did. And that wanting is poison to a careful measurement because there are 1,000 small choices in the work. Where to draw a line, which data to trust, how to handle an odd run, and a person who knows which way the answer should go can nudge each of those choices without meaning to, toward the answer they crave. So they hid the answer from themselves. The trick is called a blind analysis, and it is exactly what it sounds like. Before any of the real work began, the rhythm at the center of the whole measurement, the speed of the muon's wobble, was secretly shifted by an unknown amount. A value was locked in a sealed envelope, in a sense, known to no one on the team. Every analyst worked with a number that was deliberately wrong by that hidden offset. They could polish their methods, hunt down errors, and argue about every choice, all without ever seeing the true result. They were flying with the windshield painted over. This let them be honest in a way that willpower alone could never manage. With the real answer out of reach, there was no point in nudging anything toward it, because they could not see where it was. They could only do the work as well as possible and let the chips fall. They cross-checked each other. They split into separate groups that analyzed the same data with different methods and were not allowed to compare answers until each was sure of its own. They argued for years over tiny effects. The way the muons drifted, the way the detectors aged, the faint breathing of the magnet with temperature. Only when every group had locked down its work and sworn that nothing more would change did they hold the unblinding. They gathered, sometimes in a room together, sometimes watching from around the world, and someone revealed the hidden offset. The painted windshield cleared. In a single moment, the deliberately wrong numbers everyone had been staring at slid over to their true values. And the real answer, the thing 6 decades of work had been driving toward, appeared all at once. It is a brutal way to live. You spend years on the most important measurement of your career, and you are forbidden, by your own design, to know what you are finding until the very end. But it is the only way to be sure that the number you finally report is the universe talking, and not your own hope whispering back at you. So the ring was ready. The beam was ready. The analysis was locked. The offset was about to be revealed. Either the muon would shrug off the old result and slide back into line with the theory, quietly ending the whole affair, or it would do again what it had done in country after country and decade after decade, and hand back the same defiant gap. What happened in that room would decide whether the field was chasing a ghost in the math or a crack in reality itself. In a packed auditorium, with screens carrying the moment to people watching all over the world, someone finally read out the hidden offset. For years, the team had worked with a wobble speed that was wrong on purpose, shifted by a secret amount none of them knew. Now the secret was spoken aloud. Analysts typed it into their code. The deliberately wrong value slid away, and the true value of the muon's extra appeared, all at once, for the first time. It landed almost exactly where the old result had said it would. The colder ring on the far coast had measured the muon to wobble a sliver, more than the theory allowed. Now the same ring, hauled across a continent and rebuilt in Illinois, fed by a purer beam and read by fresh detectors and a new team of people who had hidden the answer from themselves, came back with the same sliver. The two results sat almost on top of each other. There was cheering in the room, the kind that comes from years of held breath. But the deeper meaning was colder than the celebration. Think about what had just happened. A new machine, in a new place, run by different people using different methods, with the answer locked away until the final second, had reproduced a result that the rest of the field half expected to melt away. The gap had not melted. It had been confirmed by a wholly independent look. When the two measurements were combined into a single world value, the muon's extra sat above the leading prediction of the day by more than 4 steps. 4 sigma. Not yet the 5 that the field demands before it will say the word discovery, but closer to that line than anyone had ever been. And it was no longer one experiment's lonely claim. It was 2 generations of machines agreeing across a span of years and a continent of distance. For a stretch of time, this was the most exciting number in physics. If the muon really was wobbling more than every known particle could explain, then something unknown was leaning on it from inside the haze. A new force too feeble for us to have noticed. A heavy particle too shy to appear in any collider we had built. Some hidden corner of reality making itself felt only through the spin of a dying particle. The gap was a fingerprint, and the owner of the fingerprint had never been seen. Papers poured out. Theorists who had spent careers dreaming up new particles found that their inventions could, with the right tuning, supply exactly the missing push the muon seemed to feel. The measurement had become a target that 100 ideas about new physics were suddenly racing to hit. And yet, in the quieter parts of the field, a different worry was growing louder. Remember what the gap was made of. It was the difference between 2 numbers, the muon's measured wobble and the theory's predicted wobble. The measurement was now rock solid, checked and rechecked, hidden from its own makers until the end. The prediction was something else. The prediction leaned on that one stormy term, the boiling of the strong force in the vacuum, the single piece nobody could compute cleanly and everybody had to estimate. So a sharp question started to spread. The experiment had done everything right. But what if the theory's number, the thing the muon was being compared against, was the part that was wrong? What if the gap was real, repeating, stubborn, and yet pointing not at a new particle, but at a mistake in the hardest calculation anyone had ever attempted? The only way to know was to push the measurement even further, and to drag that stormy term into the light. The team did not stop at one result. A measurement that important has to be hammered on until it either breaks or refuses to. So they kept the ring running and kept the beam pouring in. And they gathered far more muons than the first round had used. Then they did the whole grim ritual again. They hid the answer from themselves, split into rival groups, argued over every faint effect, and only at the end revealed the offset and let the true value snap into place. It snapped into the same spot. The number barely moved. What changed was the fuzz around it. With more muons counted and the field mapped even more carefully, the cloud of uncertainty shrank, and the measured value of the muon's extra grew sharper than ever. The gap with the leading prediction did not soften. If anything, with the tighter measurement, it stood out more clearly. The muon was wobbling more than the known universe could explain, and now it was saying so with a steadier voice. Hold the pattern in your mind, because by now it has happened so many times it should raise the hair on your arms. the borrowed magnet long ago, the sharper machines that followed, the cold ring on the far coast, the first unblinding in Illinois, and now this second, sharper look. Every single time, across more than half a century, the muon has handed back a number that sits a little above what the theory allows. Different people, different decades, tools that improved beyond recognition, the same defiant sliver, again and again. This is the part that separates the muon from the long graveyard of results that excited physicists, and then vanished. Most hints fade. You measure again, and the bump shrinks, the gap closes, the ghost turns out to be a trick of the light. This one does the opposite. The more carefully it is measured, the more firmly it plants its feet. It behaves exactly the way a true feature of reality would behave, and not at all the way a fluke does. But the people doing the work were not allowed the comfort of belief. They knew that a result which repeats perfectly can still be the faithful echo of a shared mistake. If every prediction leaned on the same flawed estimate of the strong force storm, then every comparison would show the same gap. Honestly, forever. And it would mean nothing about new particles. The repetition on the experiment side was airtight. The repetition was not the problem. The problem was the lonely, contested number on the other side of the comparison. So, while the experiment kept tightening its grip, a second contest was heating up, away from the ring, among the people who calculated the prediction. They had realized that the entire question, new physics or no new physics, now rested almost entirely on their shoulders, and specifically on how they handled the storm. And they were beginning to disagree with each other, sharply, about how big that stormy contribution really was. That disagreement was about to grow into the strangest twist in the whole affair. Because while the experiment had been busy confirming the muon's wobble over and over, the prediction it was being compared against had quietly started to move. For a long time, the prediction had a single accepted value. An international group of theorists, the keepers of the official number, had gathered up the best estimates of every contribution to the muon's extra, including that troublesome strong force storm, and stitched them into one agreed prediction. That number was the line the muon kept jumping over. It was built mostly from the clever sidestep, the method where you measure the storm indirectly by smashing light particles together and watching the strongly interacting debris fly out. Then the ground shifted under that number, and it shifted because of a completely different way of attacking the storm. A separate group of physicists had been working for years on a method that did not lean on any of that debris data at all. Instead of measuring the storm in the real world, they set out to compute it from the bare rules of the strong force, directly, using some of the most powerful supercomputers on the planet. It is a staggeringly hard thing to do, and for a long time it was not precise enough to matter. But the machines kept getting bigger and the methods kept getting smarter, and eventually this group produced their own value for the storm, built from first principles, with a precision good enough to take seriously. Their number did not match the official one. It was larger, and the size of the difference was not a footnote. When you fed their bigger storm into the muon prediction, the predicted wobble rose. It rose by just about the amount needed to close the gap. In their calculation, the muon was not wobbling too much at all. The known universe could account for the whole thing, with no new particle required, no hidden force, nothing leaning from the dark. The gap, in their telling, had never been a crack in reality. It had been a shortfall in the old estimate of the storm. Stop and feel how strange this is. Two groups of careful, honest physicists, working on the same quantity, the same single number that decides whether new physics exists, came up with answers that disagreed with each other. not the experiment disagreeing with the theory disagreeing with itself. One method said the muon was crying out for new physics. The other said the muon was behaving perfectly, and the only thing crying out was the old way of doing the math. This was, in some ways, worse than a clean discrepancy. A clean gap between measurement and theory is a mystery you can chase. A split inside the theory means you cannot even say what the muon's wobble is supposed to be compared against. The target itself had blurred. Until the two methods could be reconciled, the muon's stubborn number was a riddle without a fixed answer, because nobody could agree on what the universe predicted in the first place. So the whole drama quietly relocated. For decades, the suspense had lived in the ring, in whether the muon would wobble more than expected. Now the suspense moved onto the page, into a fight between two ways of counting the storm, one rooted in real collisions, the other born inside a supercomputer. To understand why they disagreed and which one to trust, you have to look at both roads, and at how two honest methods could arrive at two different truths about the same patch of empty space. There are two ways to find out how hard the strong force storm tugs on the muon, and they could hardly be more different in spirit. The first road is the old, trusted one. You go out into the world and you measure. Somewhere in a laboratory, you take electrons and their mirror twins and smash them into each other head-on, and you carefully record the strongly interacting debris that sprays out. The deep logic of physics ties that debris directly to the storm the muon feels, so by measuring one, you can pin down the other. People have been collecting this collision data for a long time, across many machines and many energies, and combining it all into a single estimate of the storm. This is the data-driven road. Its great strength is that it is anchored in real measurements of the real world. Its great weakness is that it is only as good as the experiments that feed it, and those experiments do not always agree with one another. The second road is the one born inside computers. Here you do not measure the storm at all. You take the fundamental rules of the strong force, the bare laws that govern how its particles grip and swarm, and you simulate empty space directly. You chop a tiny patch of space and time into a fine grid of points, and on every point you let the strong force do its churning, and you let the largest supercomputers in the world grind through the impossible bookkeeping. Out the far end comes a value for the storm, built from nothing but the underlying laws. This is the road from first principles. Its great strength is that it leans on no outside collision data at all. Its great weakness is that the calculation is so monstrous that for years it was too rough to settle anything. For a long time, the data-driven road ruled, because it was the more precise of the two. The official prediction, the line the muon kept clearing, was built on it. And on that road, the muon's wobble looked too large. New physics seemed to beckon. Then the computer road caught up. The simulation sharpened, the machines grew, and the first really precise result from first principles arrived. It gave a larger storm than the collision data did, large enough to lift the prediction and swallow the gap. Suddenly there were two roads to one number, and they did not meet. The road built from real collisions said new physics. The road built from pure law said the standard model was fine. When two careful methods disagree, one of them is missing something. Either the collision data had a flaw, some measurement quietly off, dragging the storm too low, or the supercomputer simulations had a hidden bias, some subtle error in how they carved up space, nudging the storm too high. Both teams were scrupulous. Both had checked their work for years, and both could not be right. This is the kind of disagreement that does not get resolved by argument. It gets resolved by going back to the source and looking harder. And the source, on the data-driven road, was the collision experiments themselves, the machines that smashed those mirror twins together and counted the debris. If the storm really was bigger than that data had been saying, then somewhere in those collisions, a measurement was off. The way to test it was to do the collisions again, with a fresh machine and a fresh team, and see whether the debris came out the same. A laboratory far from either ring, with exactly that kind of machine, was about to do precisely that. And what it found would push the two roads toward each other in a way nobody had ordered. In a laboratory in Russia, in a city built for science out in the cold expanse of Siberia, there sits a different kind of machine. It does not store dying muons. It collides electrons with their mirror twins, the same kind of collision that feeds the data-driven road, and it measures the strongly interacting debris that comes flying out. It is one of the long line of experiments whose results get poured into the official estimate of the storm. And a team there decided to remeasure one of the most important of those collisions with more care than anyone had managed before. The piece they focused on is the single largest ingredient in the whole storm. When the mirror twins collide at just the right energy, they often produce a particular pair of strongly interacting particles, and that one outcome dominates the muon's strong force, tug more than any other. Get that one collision right and you have nailed most of the storm. Get it wrong and your whole estimate is off. So they measured it again, and they measured it hard. Their answer did not match the older collision data. It came out higher. The pair was produced more often than the previous measurements had said. And a higher rate for that collision means a larger storm, which in turn means a larger predicted wobble for the muon. In other words, this fresh look at the real world pushed the data-driven road up, toward the value the supercomputers had been claiming all along, and toward the muon's measured wobble. On this new collision data, the gap shrank toward nothing. It would be a tidy ending if that were the whole story. It is not. And the messiness is the point. Because the new collision result did not just disagree with the muon prediction, it disagreed with the other collision experiments, the ones that had built the official estimate for years. So now, the trouble had burrowed even deeper. It was no longer only the two roads, collisions versus computers, that disagreed. The collision data disagreed with itself. One careful experiment said the storm was small. Another careful experiment said it was large. They could not both be measuring the same universe correctly. This is the unglamorous reality of science at the edge. There was no villain, no obvious blunder, no one caught with a thumb on the scale. There were only several scrupulous teams, each confident in its own work, handing back numbers that would not line up. Somewhere among them an effect was being missed. Some quiet bias in how the debris was counted, or how the machine was understood. Nobody could yet say where. But step back and look at the direction everything was drifting. The supercomputer road said the storm was large. The newest, most careful collision experiment said the storm was large. Two independent lines, one from pure law and one from fresh measurement, were now pointing the same way, and that way closed the muon's gap. The old, smaller estimate, the one that had made the muon look like a herald of new physics, was starting to look like the odd one out. The walls were closing in on the exciting interpretation. And the most powerful push of all was still coming from those simulations. From the strange enterprise of building a piece of the vacuum inside a machine and asking it how hard the storm blows. To grasp how a computer can settle a question about the real universe, you have to picture what these simulations actually do, because it is one of the boldest things in all of science. The strong force up close is a churning mess that no pencil can follow. So instead of trying to track it smoothly, the physicists cheat in a disciplined way. They take a tiny box of space, smaller than a single proton, and they freeze a slice of time alongside it. And they chop the whole thing into a grid, a lattice of points, like the corners of a vast three-dimensional checkerboard. They do not let the strong force live everywhere. They only let it live on the points of the grid and along the lines between them. This turns an impossible smooth problem into a merely gigantic countable one. Then they let the vacuum boil. On that grid, they instruct the machine to play out the bare laws of the strong force, conjuring up the churning sea of particles that flickers in empty space in every possible arrangement, weighted by how likely each arrangement is. There is no shortcut. The machine must sample staggering numbers of these possible vacuums and average over them, because the real vacuum is the blur of all of them at once. This is why it takes the largest supercomputers on Earth, running for the better part of a year, to produce one number with enough digits to matter. And here is the trick that makes it trustworthy. The grid is fake. Real space is not a checkerboard, and freezing time is a lie the method tells to make the sum possible. So the team runs the whole monstrous calculation many times over, with finer and finer grids, the points packed closer and closer together, creeping toward the smoothness of real space. They watch how the answer drifts as the grid tightens, and they follow that drift to the place it would reach if the points were infinitely close, which is reality. They do the same dance with the size of the box and with other small lies, removing each one in turn until what is left is, as near as they can make it, the honest verdict of the strong force itself. When the leading group finished this ordeal, their value for the storm came out large enough to lift the muon's predicted wobble until it nearly touched the measured one. And crucially, they had used no collision data at all. They had not borrowed a single number from any other experiment. They had asked the bare laws of nature, and the laws had answered that the muon was behaving exactly as it should. For a while, a single such result is easy to doubt. A lone calculation, however heroic, might hide a bias. But then other groups on other machines, with their own grids and their own methods, ran the same gauntlet, and their numbers came in close to the first. The agreement among independent simulations grew year by year until the large storm was no longer one team's claim, but a chorus. So now, 2 of the 3 lines stood together. The simulations, built from pure law, and the newest collision experiment, built from fresh measurement, both said the storm was large and the muon was innocent. Only the older collision data still held out for a small storm and a guilty muon. The weight of evidence had begun, slowly and against everyone's early hopes, to swing toward the dullest possible answer. Watch what happened to the gap over the span of just a few years, because the shape of it tells the whole story. At the start, the picture was thrilling. The muon's measured wobble sat above the official prediction by more than 4 steps, and as the measurement sharpened, that distance pushed past 5 steps against the older prediction. 5 sigma is the magic line, the threshold the field calls discovery. For one glorious moment, it looked as if the muon had carried us across it, as if a new piece of reality had finally been forced into the open by a dying particle in a ring. Then, the prediction started to move, and the gap began to collapse. Not because anyone changed the measurement. The muon's wobble stayed exactly where it had always been, confirmed and reconfirmed. The gap shrank because the thing on the other side of the comparison, the predicted wobble, climbed upward as the large storm gained support. Each new simulation that agreed on a big storm lifted the prediction a little closer to the measurement. The fresh collision data lifted it further. Step by step, the distance that had once breached 5 sigma fell back toward 4, toward 3, toward 2, and kept falling. The keepers of the official number could not ignore what was happening. When the evidence for the large storm had grown strong enough, they did something that quietly ended an era. They built a new prediction, and in it they leaned on the supercomputer consensus for the storm instead of the old collision estimate. With that one change, the predicted wobble rose to meet the muon almost exactly. The new official line sits only about 1 step away from the measured value. 1 sigma. Comfortable agreement. The kind of match that anywhere else in physics you would call a quiet success and move on from. So the great anomaly, the stubborn gap that had survived more than half a century, that had been hauled across a continent and hidden from its own measurers and confirmed again and again, did not survive being recalculated. The error that kept repeating in experiment after experiment turned out, most likely, to have a twin that kept repeating in calculation after calculation. The muon was probably never wobbling too much. We were probably just adding up the storm too small. This is a deflating thing to say plainly, and the honest scientists at the center of it say it plainly. The most likely explanation for the muon's gap is not a new force or a hidden particle. It is that the hardest number in physics was, for decades, slightly off, and that the muon was telling the truth the whole time while our prediction lagged behind. But notice the word likely, and notice it carries weight. The case is not fully closed, because the collision data still argues with itself, and a disagreement among honest experiments is not a thing you can wave away. The small storm has not been proven wrong so much as outvoted. Somewhere in those collisions, an effect is still unaccounted for, and until it is found, a sliver of doubt remains. Yet the direction is unmistakable, and it points away from the dream. The muon, which for years looked like the most promising doorway to physics beyond the known, has very nearly closed that door with its own steadiness. And the newest verdict, the latest and most precise reckoning of all, pushed the door almost flush against the frame. The most recent calculation to land did not nudge the gap. It nearly erased it. A team brought together the sharpest tools the field had developed, the matured supercomputer simulations, and the best understanding of every contribution to the storm, and produced a prediction for the muon's wobble more precise than any before it. When they set their number beside the measured one, the two agreed to an astonishing depth. The predicted wobble and the real wobble matched out to many digits in a row, and the gap between them fell to about half a step, half a sigma. In the language of this field, that is not a discrepancy at all. That is a bullseye. Sit with what that means. The muon's extra is now one of the most thoroughly tested numbers in the history of science, attacked from the experimental side by 6 decades of ever finer measurement, and from the theoretical side by the largest computers ever built. And when the two finally meet, at the limit of everyone's ability, they shake hands. The known universe, with no new particle added, no hidden force invented, accounts for the muon's behavior down to a precision that would have seemed like fantasy a generation ago. The doorway that the muon seemed to open has very nearly swung shut. The strongest single hint that there might be undiscovered physics out there, the gap that launched 1,000 papers and justified hauling a giant magnet across a continent, has dissolved into agreement. Not because the measurement failed. The measurement was magnificent and honest from the first crude attempt to the last. The agreement came because the theory finally caught up to a particle that had been right all along. There is something almost unbearable about that, and it is worth feeling rather than rushing past. For years, the muon's stubborn wobble was the great hope of the field, the live wire, the place where the rulebook seemed to be missing a page. Physicists need the rulebook to be missing pages. The whole enterprise runs on the faith that our current theory, magnificent as it is, cannot be the final word, because it leaves enormous things unexplained. The muon was a crack in the wall, and through that crack, people thought they might glimpse what lies beyond. The newest verdicts spackled the crack over, and yet the case will not fully close, and the people closest to it are careful to say so. The collision data still disagrees with itself, and that unresolved fight is a loose thread hanging out of an otherwise tidy garment. Pull it the wrong way and the whole picture could shift again. A small chance remains that the large storm is the mistake, that some subtle bias has crept into the simulations and the fresh collisions alike, and that the muon really is wobbling too much after all. The agreement is overwhelming. It is not eternal. Science does not deal in eternal. But strip away the hope and the hedging and look at where we actually stand. A particle that lives for 2 millionths of a second has been measured wobbling over and over by people who could not have met, and the number has never wavered. We compared it against everything we know, and after a long and bruising fight, everything we know turned out to be enough, which leaves us facing two possibilities, and it is hard to say which one is more frightening. The first possibility is the one the evidence now favors, and it is bleaker than it sounds. It says the muon's gap was our mistake, that the standard model predicted the wobble correctly all along, and that there is no hidden particle leaning from the dark. Taken alone, that is a story of triumph, our theory vindicated against its toughest test. But carry it to its end, and the triumph curdles. Because the standard model, for all its perfection, is known to be incomplete. It says nothing about the gravity that holds you in your chair. It offers no account of the unseen matter that outweighs every star, or of the strange energy that is pulling the universe apart faster and faster. It cannot explain why the cosmos is made of something rather than nothing, why matter survived and its mirror twin did not. The theory we keep confirming is a theory we know cannot be the whole truth. We are certain there is more. We simply cannot find where it hides. The muon was one of our best maps to the hidden country. It pointed for years at a door. If that door has closed, it does not mean the hidden country is gone. It means our map just lost its clearest landmark. The new physics we are sure must exist has slipped back out of reach, leaving us inside a theory that works beautifully and explains far too little. That is the first nightmare. Not that we are wrong, but that we are right. And being right gets us no closer to the things that matter most. The second possibility is the opposite and no gentler. It says the large storm is the error, that the simulations and the fresh collisions share some quiet bias, and that the muon really is wobbling more than the known universe allows. In that case, the gap is real after all, and something genuinely new is out there, tugging on the muon from inside the haze. That sounds like the happy ending, the door flung open. But think about what it would mean for how we know things. It would mean that the most carefully computed number in physics, checked by independent supercomputers and confirmed by a fresh experiment, was wrong in a way that fooled the best people in the world for years. It would mean our ability to calculate the universe is shakier than we let ourselves believe. So here is the shape of it. Either our theory is right and our hope for something beyond it has gone quiet, or our hope is alive and our theory is less trustworthy than we thought. A complete and sterile universe, or an incomplete and uncertain one. Pick your dread. The muon does not care which you prefer. What makes this genuinely unsettling, more than any single answer would be, is that we cannot yet choose between them with confidence. We have measured one number to the edge of what is possible, and we still cannot say whether it is the sound of a wall or the sound of a door. The most precise comparison in all of physics ends not with certainty, but with a fork, and both paths lead somewhere uncomfortable. Through every twist of this long argument, one thing has stayed perfectly still, and it is the one thing we never doubt. The muon's wobble. The number itself. While the theorists fought and the predictions rose and the gap opened and closed, the particle in the ring kept handing back the same answer it had given for 60 years. Without complaint. Without drama. Without a single lie. Go all the way back to the beginning of this, to the borrowed magnet and the small team who first pinned the muon's wobble to a couple of percent. Lay their number next to the latest one, read by detectors they could never have imagined, in a ring hauled across a continent, compared against a calculation run on machines that did not exist in their lifetimes. The precision has improved by a factor you can barely picture. The story around the number has lurched from agreement to anomaly to agreement again. And the number itself, the muon's actual extra, has sat in the same place the entire time. That is the quiet center of the whole affair, and it deserves to be named clearly. The muon never wobbled too much, and it never wobbled too little. It always wobbled by exactly the amount the universe makes it wobble. Every crisis in this story, every gap and every fix happened on our side of the line. The disagreement was never between the muon and reality. It was between the muon and our description of reality. The particle was a perfect witness from the first crude measurement onward. We were the ones who kept misjudging what its testimony meant. The title of this whole story speaks of an error that keeps repeating, and now you can see what that error really was. The thing that repeated, across machines and decades and continents, was not a flaw in the universe. It was the gap between a flawless measurement and an imperfect prediction. And the reason it kept repeating is the most ordinary and most profound reason in science. The measurement was honest, and our math was still catching up. Every team saw the same gap because every team was comparing a true number against an estimate that was slightly off in the same direction. The repetition was real. The error lived in us. There is a strange dignity in that. We tend to imagine science as a march of human cleverness conquering a passive world. Here it was the other way around. A particle too small to see and too brief to hold sat patiently in a magnetic field, telling us the same true thing for the length of a human career, while generation after generation of brilliant people argued over whether they had understood it. The muon was not the mystery. We were. And this is why the field is not crushed, even as the great anomaly fades. Because a number that refuses to lie, no matter how hard you push on it, is the most valuable thing a scientist can own. It is a fixed star to steer by. Every time we measure it more precisely, we sharpen the blade we use to test everything else. The muon's wobble has become a ruler so fine that the faintest new particle, if one is hiding in the haze, would eventually bend it. The door may look closed today, but a ruler that exact will keep being held up against the theory for as long as physics is done, and if there is a crack anywhere within its reach, it will be the muon that feels it first. So, the witness keeps testifying, patient, exact, indifferent to our hopes. And the most remarkable thing about it is not in any laboratory at all. It is happening right now in the space where you are sitting. Look up from this, just for a second, and consider what is passing through the room. The moons are still falling. They are streaming down from miles overhead, born in the wreck of cosmic debris hitting the top of the air, raining through the ceiling and through you and on into the ground beneath your feet. About one of them slipped through your outstretched hand every second. They do not slow down for skin or bone. They were never made for you. They are simply on their way through, and every one of them is wobbling. Each muon tearing through your body right now is a tiny magnet spinning in the faint field of the Earth. And it carries the same extra, the same little surplus above 2, that the borrowed magnet measured long ago and the Great Ring measures still. The number that swallowed 60 years of human effort is not locked away in a laboratory. It is written into every one of these particles identically as they pass through your chest without a sound. The universe is performing the experiment everywhere, all the time, and getting the same answer it always gets. That is the thing to hold on to. We built giant machines and hauled them across continents and ran the largest computers on Earth for the better part of a year, all to read a number that the sky is handing out for free, 1 million times over, through every living body on the planet. We went to extraordinary lengths to ask the universe a question it has been answering out loud since long before we existed. And the answer never changed. It does not depend on us, or on whether we ever understood it. What we still cannot say is what the answer means. We have measured it to the edge of the possible, and we are left standing at a fork. On one path, our theory is complete to a degree that should thrill us, and instead leaves us locked inside a description that cannot explain the dark weight of the cosmos or the energy pulling it apart. On the other path, something new is hiding in the haze, and our finest calculations have been quietly fooling us. A wall or a door? The muon will not tell us which. It only keeps wobbling, exactly as much as it always has, through the ring, through the sky, through you. We thought we had found an error in reality. What we found was a number too honest to bend, and the slow discovery that the error was always on our side of the glass. That should be a comfort. Mostly it is. But somewhere underneath the comfort sits the part that does not let go. We have questioned the universe as precisely as it is possible to question anything, and it answered without hesitation, the same way every time. We just still don't know what it said.